Okay, in this presentation we are looking at a statistics with R presentation. This is an introduction to R for actuarial students. This follows the CS1B curriculum. That's a course that has an introduction to R programming component as well as a fundamentals of statistical analysis. This particular presentation is question 4 from this actual playlist, this paper series, and it's on regression analysis, bivariate analysis. So the question is as follows. A recent study suggests that the maximum heart rate of a person related to age in years is given by the following equation. So the max rate equals 220 minus age. Suppose this is to be empirically proven and 15 people of various ages are tested for their maximum heart rate. Okay, so this is the data that we collect. We have 15 people, we have their ages, okay, on the top, and the maximum rate down here. So the data can be entered into R using the following commands. So essentially just combine all of the numbers into a single object using the C command, and we just call them X and Y for the time being. So what we're going to do, the first thing we're going to do is plot the fitted line for the regression of maximum rate on age, X and Y. So just before we begin, what we'll do is actually just plot the scatter plot of the points. Okay, so this is the command, plot X and Y. The rest of it is just to make the plot easy to look at. PCH equals 18, that's the plot character, color equals red, and the character size equals 2. CEX is the character size, that's equal to 2. So that's the scatter plot that we would get. You can see the downward, from the top left to the bottom right, that downward trend in the points. Okay, now it looks like a very close relationship, a very compact, you know, what's going to come around the trend line, the regression line. Anyway, let's just see if we can put the regression line on top of that. Okay, so first off I have to create my regression model. The command here is lm, and we're going to explain y by x. Okay, lm y explained by x, and we're going to save this as linear model.result. Okay, now if I just want to look at the values, see what happens, I get this here. So this is the intercept and the slope. 210.04 and minus 0.797. Okay, so the baseline is 210, and for every year older you are, it goes down by a minus 0.79. So, you know, there we go. Now, so this is what I plotted before here. Okay, so what I'm going to do here is just add the regression line to that plot. Okay, so just adding in this bit here. Abline, just specify the regression model, and just to make it easier, I'm just going to color it in red. In fact, I have this changed so the points now are blue and the trend line will be red, the regression line will be red. Abline is something that creates, adds a line to an existing plot, essentially. Okay, so that's what we got there, and it looks like it's a very good, well-fitting model. Okay, the points, the scatter plot points tend to be clustered very closely around the regression line, which is a great sign. So this is the summary of the linear model, summary.lm, and we're just looking down here at this. The multiple R squared is 0.9091 and the adjusted R squared 0.9021. These are goodness of fit metrics, R squared essentially. It just actually tells us how well the model explains the variation in the data. And it's a number between 0 and 1, or 0% and 100%. And anything close to 100% is considered pretty good. The closer you are to 100%, the better. Okay, that's good. So our conclusion is that the max heart rate reduces as age increases, and the fit of the model seems to be quite good. So just a couple of other useful commands. We can actually take out the regression coefficients directly. So we can, if we want, this is just two useful functions to know. Coef, which is coefficients of the linear model, lm.results, that's the one we have fitted. There we have them there, 210.048 and minus 0.7977. If we want a confidence interval for those coefficients, we can just use confint to specify the name of the model, and this provides a confidence interval, a 95% confidence interval for the regression coefficients, the intercept estimate and the slope estimate respectively. You'll just notice here that that range of values does not include -1. Okay, that's important. So comment on the results. Okay, so I've just sort of done that really. So a researcher reviews the plot in exercise 1 and suggests the slope should be equal to -1. Okay, and we've already seen that it is not. It is between, well, it's not, as far as the confidence interval is concerned, that the indication is that it's closer to 0. You know, it's closer to minus 0.77. Okay, 7977. Okay, so it's not. What we're going to do is calculate the p-value of hypothesis test for this suggestion by creating a suitable test statistic. We can do a test to see if the slope of -1 is correct. The population value is -1. So let the null hypothesis H0, let that be that beta, the true value of beta, equals -1, and the alternative is that it is not equal to -1. Okay, so then we can create the test statistic and the p-value as follows. Now, there's a good bit of work to this. There is no OR command that really helps you with this. You have to sort of just build it up yourself. And this is sort of using all of the building blocks from OR. Okay, so what we're going to do is get the errors. This is residuals, actually. Okay, so this collects up the residuals from the linear model, and we can have a look at them there. Epsilon's actually just the error terms. And this is the difference between the observed value and the fitted value. Okay, we can also take out the slope estimate. Okay, so using the coef command that I had a look at earlier and just sort of specifying the x element that just picks out whatever is called x, whatever has the name x, and the value attached to that, and there we go. So we should get minus 0.798, that's the beta value, and n is just 15, it's just the number of observations. That's relevant because that actually tells us the degrees of freedom later on. Now, this is where a little bit of theory comes in. Okay, so this is not really our stuff, but if you're going to be doing this, you have to sort of remember what all of this is about. The residual standard error and the mean squared error. Under the assumption that the population error term has a constant variance, the mean square error, MSE, of the regression is the estimate of the variance, that variance, and is given by sigma hat squared epsilon, okay, equals SSR, the sum of squares for residuals, divided by n minus 2. Okay, and the residual standard error is what we're going to be using is simply the square root of that. Okay, so this is straightforward enough really. We can just get we have our residuals, square them and sum up the answer, and then divide by n minus 2. To get the residual standard error, we just get the square root of that. That's great. So the answer there is 4.578. Okay. Just as a quick remark, there are other ways of doing this. Now, I won't really get into this, but you can actually build this up from other ways without using residual terms. So the deviance divided by the df residual lm. I won't get into that, but put it this way: there's other ways of approaching this problem that, you know, when you get used to the deviance and this sort of stuff, you know, you might be a bit quicker at this. Okay. But anyway, we'll sort of go with the main approach here, the sort of very simplistic approach, this approach here. And our answer, our intermediate estimate for the value we're going to need is 4.577. Now, the standard error of the parameter estimates are given as follows. So we actually need this one here, okay? And it is the residual standard error times the square root of 1 over the sum of xi minus x bar squared. Okay, So this is not too bad actually. Just as a quick remark, what we're doing here is dividing, okay? So S divided by, so that here it's a multiple, but I'm just going to divide it as, it's just a slightly different way of the formula, just be careful about that. So divide by the square root of this term here. Okay, that's all I'm doing. And this gives our standard error, and that is 0.06999. Okay, so the test statistic simply is the observed value minus the hypothetical value under the null hypothesis, the value proposed by the null hypothesis, divided by the standard error. And this is a t-random variable, okay? So our test statistic is essentially 2.8911, and we find the right tail from this with this value of t, this t random variable, with 15 minus 2 degrees of freedom, okay? So pt of t, 13, lower tail equals false, and this gives us 0.00631, okay? Now this is a two-tailed test, so essentially what we do to get the p-value is double that, and we get a p-value of 0.0126, okay? So in this case, what we're going to do is reject the null hypothesis. The true slope is not equal to 1, minus 1, okay? And therefore, you know, it's close, but it's not close enough. Put it that way. Okay, we'll leave it there.